Here we'll be covering linear systems of differential equations. This is where the actual model of the system we have is in the form of rates of change. So the overall system is not linear in nature, but one form of representation of it is. Wondering why we would have a system of differential equations. Usually when we're modeling things, we're just modeling the variables and some relationships, linear and nonlinear. But that's in an empirical sense, so that's when you're measuring lots of values over time, collecting the data, and then you try and fit an equation to it. So there's another way, which is more common in systems where there's a very physics-based representation of it, and we understand what causes relationships between variables. We just don't know the exact relationship. So this is the rate of change. The rate of change is often, if with y and x, on average, delta y on delta x. In the case we're dealing with, we're using instantaneous rate of change, so it's just at an instant point in time. And that's either represented as dy on dx or f dash of x. Usually it's time, so f dash of t. And basically at each different points in time for this system in the real world, we're seeing what the value of those are. So maybe t1 and then t3, and we're seeing how do these relate. Change with differential systems is exponential. So this is the form of some combination of e to a function. Usually e to the x is the most basic. And this occurs when the growth or decay of a quantity is proportional to that current quantity. So as the total quantity increases, so does the rate of change. This results in very sharp gradients, and the gradient is the same thing as the instantaneous rate of change here, f naught time. So this occurs in pretty much here and here. They're populations of something growing. So human population growth, bacteria, cancer, and it also comes into account with finance, so inflation and compound interest. And just so you know for the next slide, the derivative, so the rate of change of a function e to the x, or a e to the x, is, a e to the bx is a times b times e to the bx. In other words, f naught of x equals a times f of x. It's a proportional relationship. Exponential functions have linear combinations of themselves for derivatives, and this isn't just the case of their own function. So you might have f naught equals a f plus b g, where f and g are functions. And if you have a few of these equations, like g naught equals q f plus p g, and this is all in one system, you can see it's forming a standard linear equation where here you've got your, what's usually the b vector, these coefficients here go in the matrix A, and then f and g are like x1, x2, or x and y. So you end up with an equation over here very similar, or the exact same, just we proceed in a different order. So the f naught vector is equal to the coefficients matrix times the actual functions themselves. Proof for how this general solution to that form of linear equations is found, but it's fairly straightforward using diagonalization and some parameter swapping. But anyway, it's in form of the eigenvalues and eigenvectors. And then as you can see here, C1, C2, Cn, that is a constant that you find by substituting known values. So you would usually be given a set of values that are true just from recording the system, and you sub that in to find them once you know the rest. But just for the sake of time, I've written this out. So here we have a sample equation that will be easy to solve, where it's already a diagonal matrix, so the eigenvalues are the diagonals 3 and 2. As you can see there, that's how it's formed. And for the eigenvectors, it's 1, 0, and 0, 1. When you plug these in, you get fairly simple ones where when you multiply through these constants, you have C1 times e to the 3x plus c2 times e to the 2x. And basically what that is the first one is f1, the second one is f2, because remember, f of x here is actually a vector function. So once you multiply those through, you plug in the values for c, and then you have the equation in the general form, which is much faster than going through and trying to solve each one with standard calculus, at least in this scenario.